almost.
Okay.
Used to be easier when there was just...
Samson Abramsky from Oxford University will speak about propositional calculus and the nature of reality.
Thank you. Yes. Yes, after following Perkion's beautifully coherent and well-organized talk, mine is going to be less so. So let me begin with my excuse, which is that when Benedict contacted me a few days ago to say he wanted this talk, I sort of told him I was hard-pressed, just coming back from a meeting and so on and so forth. But behind his gentle exterior, Benedict is quite remorseless, so he insisted, and I'm giving this talk. But if there's a bit of undue levity in it, starting with the title, then I sort of feel a certain abdication of responsibility because it was Benedict what made me do it, so I'll blame it on him. Okay, so yes, so propositional calculus and the nature of reality. I actually rather like this title. When I first learned logic, propositional calculus was regarded as the really trivial part of logic. But it's kind of had the last laugh, hasn't it? Because if you want to win one of the Clay Millennium Prizes for something to do with logic, then propositional calculus is the way to go. But I want to look at a different aspect. So let me begin with something very simple, so simple that you may feel it hardly deserves description, and yet we'll see there's something interesting there. So we start with some propositional formulas. And I'm going to suppose further that I can assign a probability to each of these formulas. And the story that I'd like to tell, or we'd like to have in mind, is that the variables that occur in the formulas correspond to quantities that we can actually perform experiments on. So we get two-valued kinds of quantities. So each formula is just something sitting in the Boolean, the event algebra, and it's describing possible outcomes regarding experiments we can perform by measuring these quantities. And these are measurements that can be repeated, so we can perform them multiple times and obtain statistics by relative frequencies. So that's a perfectly sensible bit of basic science, so we have some probabilities. Okay, so now I'm going to do a little calculation. Perhaps the second week of Probability 101, it might be a classroom exercise. So we form the conjunction of these formulas, and we do a little calculation. So we, I don't think I'll go through this little derivation. If we tidy it up, it says that the sum of the probabilities is bounded by n-1 plus p. P is the probability of the conjunction of these formulas. Okay, everyone happy with that? Could be an exercise in week 2 of Probability 101, I think.
So isn't the sum of pi's equal to 1?
Sorry?
Isn't the sum of pi's equal to 1?
No, these are a bunch of these are just probabilities.
Okay.
So they could be anything between, each of them could be anything between 0 and 1. So of course the maximum they could be is n.
Okay.
All right? Yes, nothing, no tricks or anything. But I give you one piece of additional information. I now tell you that in fact this set of formulas is jointly contradictory, by which I mean that their conjunction is unsatisfiable. So the conjunction actually describes the null event, which therefore must get probability 0. And under that circumstance, the sum of these probabilities is bounded by n-1. Okay? Still very simple. Okay, good. So nothing to see here. But now we come to a curious observation. Quantum mechanics tells us that we can find propositions phi I describing outcomes of certain measurements which not only can but have been performed. So think of spin measurements, or we'll see an example in a little while. And they've been done lots of times, and we have very highly confirmed probabilities for these propositions. very highly confirmed probabilities. Quantum mechanics is our most highly confirmed physical theory. Moreover, the propositions are easily seen to be jointly contradictory. However, this inequality is observed to be strongly violated. Well, the maximum that this sum could be, as we said, is n, and we can find cases where it is actually n, despite the fact that we showed that it could only be n minus 1. So, my question, how can this be? So perhaps we can come back to that a little later, but it's a good thing to ponder on. I actually feel this is one of the nicest and most direct ways that I know of presenting one of the puzzling, perhaps the essential puzzling feature of quantum mechanics. So, let's think about that, but soldier on. And let me say that the equality of this form, so here I've got a bunch of formulas. As we've said, their conjunction is unsatisfiable. And I have an expression like this, where we're saying this is the probability we associate to this event. And then, as we saw, under the hypothesis of this conjunction being unsatisfiable, simple elementary probability theory gives us this bound. So we call this a logical Bell inequality. Logical because it's determined by a purely logical consistency condition. Okay, so now let's look at an example, a probabilistic model of an experiment. So the way we're to read this is that we have Alice and Bob. Alice has two possible measurement settings. So we're doing, let's say, spin measurements, something like that. Alice has two possible measurement settings, angles for her spin measurement, A and A prime. Bob has two possible settings, B and B prime. Each measurement outcome has there are two possible outcomes for each of the individual measurements. So there are four possible joint outcomes once each of Alice and Bob has selected one of their measurement settings. So we can, and they can do experiments repeatedly, get measurement statistics as we saw, and obtain a table that might look like this. Not only might they do that, but actually we can give a specific quantum state, a staple of these kind of discussions, an entangled quantum state, subjected to measurements in the xy plane, and if you get the angle between them right, you get exactly this table by elementary calculations in quantum mechanics. So this is something that can be taken as real and highly corroborated. So if we look at a table like this, well, it may make sense to us, it may not. I mean, it may be surprising or it may not. How can we tell? So the idea is to apply the little derivation that we just had to elicit some structure from this table of numbers. So in particular, let me do this. What I'm going to do is I'm going to think of the zeros and ones as outcomes as like Boolean assignments to the variables. I'm now thinking of the measurement settings, A prime, B prime as Boolean variables, and then we just get the possible assignments to those variables, right? In particular, the way in the notational convention I'll follow, I'll actually take 0 as true and 1 as false. I mean, that doesn't really matter, of course, but just so you won't be confused by the notation. Often one thinks of +1 and -1, and then +1 is -1 to the 0, and -1 is -1 to the 1, so that kind of. Now, what I'm going to do is I'm going to pick out from each row, that is, from each given choice of measurement settings, I'm going to pick out a subset of the events. And those are the ones that I've highlighted in yellow here. Okay? And I'm going to write a formula which picks out that subset as its set of satisfying assignments. So in the first row, we have the outcomes for measurement settings A and B, either 0, 0, or 1, 1. And as a formula in the variables, it's just A if and only if B. And similarly for the second and third row. And for the fourth row, you see it's the anti-correlated outcomes, and that's the exclusive OR. Okay, so now it's easy to see that these propositions are jointly contradictory. Right? Start from the bottom one. Now I can use this one to replace A prime by B, the first one to replace B by A, and the second one to replace A by B prime, and I end up with B prime exclusive or B prime. So according to the little derivation that we made on the first slide, there has to be a bound for the sum of the probabilities of these events of, well, n is 4 here, so it has to be a bound of 3. And as you can easily check, we get a violation of a quarter. So this is not an innocent table. Actually, this gives a way of proving Bell's theorem. Any offers on how this can happen, by the way? I mean, because of course, in the worst case, we could say there's a direct contradiction between logic and experience. I certainly don't believe that, and there is, but then our obligation is to go back to that derivation and say which particular step in that very innocent derivation cannot in fact be applied to quantum mechanics or to a situation like this. So anyway, we can discuss that later. All right, well, coming back to the sort of just to say a little bit about this. So there's a huge literature on Bell inequalities, but I think a lack of a sort of unifying principle. So what I've done in recent work with Lucian Hardy, who well-known figure working in foundations of quantum mechanics, quantum information, and so on, is to introduce a form of Bell inequality based on logical consistency conditions. So I just showed you the basic version of that. And it turns out that this is pervasive in this whole, although it's kind of, I mean, these things play a central role nowadays in quantum information as well as quantum foundations. But in fact, it's the case that a rational inequality is satisfied by all, in the jargon, non-contextual, or we could say more specifically here, by all local models, models that conform to the dictates of classical physics, if and only if they're equivalent to one of these logical Bell inequalities. In fact, we need something slightly more general than the form that I showed you. One needs to generalize from this kind of n formulas and bounded by n minus 1 to a notion of k consistency. So something quite analogous to the max-sat problem. So we get slightly sharper.
Yeah, so there are different logical Bell inequalities. You just saw this one, right?
Well, I showed you a general scheme. I showed you a general scheme. Any bunch of formulas, n formulas, which are not simultaneously satisfiable, and then the probabilities have to be bounded by n minus 1. So it turns out you can allow, you can have a multi-set of formulas. So let me just tell you the general scheme. You can have a multi-set of formulas, so you put weights on, and then you can have a notion of k consistency. At most k, a sub-multi-set of at most k could be consistent, and then this should be bounded by k. So that's a generalization, but a reasonably mild generalization in the spirit of max-sat, and that's what we mean in general by a logical Bell inequality, and one has this result for that. So in fact, what that tells us is that quantitative tests for contextuality or non-locality always hinge on purely logical consistency conditions, which is kind of interesting. That's particularly for logicians. Yeah, and anyway, there's some general stuff there. So that was, that's so much for propositional calculus and the nature of reality. By the way, still, let me come back to that question. Does anyone have some kind of comeback? I mean, should we maybe go back to that slide and see if we can pick any holes in our derivation? Because it is a question, isn't it? What is the inadmissible step?
Not phi is the union of it.
Sorry?
Well, is it the bounding by the sum?
You doubt that?
Well, I mean,
We don't doubt anything, but
Well, I mean, we have to doubt something.
What
But,
about the second?
but I'm not suggesting that we doubt the basic mathematics of
So what about the
probability.
second equality? Is that in
Well,
fact
You assume the models or somewhere or something like that.
Oh, so we're
negation
going
of
to doubt
the-
classical logic. You're really going to start doubting classical logic?
but
What's the database?
I mean, my usual understanding is that of violations of Bell's inequalities is that there are underlying correlations between the events.
Yeah, sure.
So-
But we're making no assumptions about these probabilities. This could be anything, right?
No,
Oh, all right, okay.
I'm just wondering whether in that sum bound there's an
Yes.
assumption that the other version,
Well,
there,
I
an
wouldn't
assumption of
say
independence.
it's quite here, but actually the place where you have to point the finger is actually when we
The second.
here. That there's a well-defined probability for this conjunction. And the point is that if you go back to those measurements, like in the table that we saw, in reality, Alice can choose a setting, Bob can choose a setting. In that subset of variables, we have a well-defined experiment. Each of these formulas here is on a subset of the total set of variables. So the question is there a well-defined probability distribution on the whole set of variables, which is going to generate the probabilities that we see empirically? And in fact, the content of all these kind of results is that there isn't. That when you have a family of these probability distributions, each defined locally on a subset of observables, you can't necessarily glue them together. And gluing together is a good language because it really does correspond to a sort of sheaf-like idea of gluing things together coherently. So actually, the legitimate thing is saying there's a well-defined distribution here where P gets this probability. Nevertheless, here we're saying that the intersection is empty, and it's hard to avoid the conclusion that the null event should get the zero probability. The thing is, there's no well-defined probability distribution that it lives in, which is consistent with all the other ones. Phew, so we don't have to give up the logical consistency, but we do see that there's something rather puzzling about, that there's some inherent contextuality about quantum mechanics. Okay, so contextuality. So picking up this idea, so in some recent work, we've shown that these ideas about non-locality and contextuality relates to the Koch-and-Specker theorem, for example, in quantum mechanics, can be handled in a uniform fashion, exactly in terms of this idea of obstructions to being able to glue together these locally defined distributions into global sections. We can even witness these things in cohomology, and as we've just seen, there's this work on how it comes out quantitatively in terms of logical Bell inequalities. And in fact, many related situations arise in computer science. And Fokion may be thinking there's no way I could relate what I'm saying to his talk, but not so fast. In fact, that one of the interesting things recently has been I've had some nice interactions with Yoko Vannanen, who I think has spent a little bit of time in this program in January. And there's some very nice connections with dependence logic. In fact, dependence logic turns out, which some of you will have seen, others perhaps not, but it's a development from the sort of stream of ideas of branching quantifiers and then the Hintiker independence-friendly logic. And dependence logic is a particularly clean and nice sort of development, now also with independence developed by Vannanen and Gradle and others. And to get a rough idea of how it works, you sort of model theoretically, you boost up the tasky semantics from single assignments to sets of assignments. Once you do that to sets of assignments, notice firstly that sets of assignments are relations, you're in the world of tables, and these dependence atoms really correspond to, the original one is a sort of, it's exactly to functional independence, and recently people have been rediscovering this wide and wonderful world that you were mentioning about joint dependencies and other kinds of dependence, and it all has a direct logical significance in the context of that logic. And it's really looking like a very nice paradigm for studying a lot of these issues. Also, it turns out a lot of, as I already hinted in the previous discussion, a lot of the discussions in quantum foundations can actually be abstracted to the relational level, and you see the same argument there. In fact, there was a sort of flow of ideas from a relational version of some of these quantum arguments that I did to the work that Yoko and Eric Gradle did on introducing a notion of independence in the sort of latest version of dependence logic. And something I discovered recently is that this sort of structure with local things over sets of variables and then trying to glue them together to get combined information Which relates to conjunctive queries in particular in databases, but also to a lot of other things as well, has been studied in a very nice unified setting by Colas and Pole. I just became aware of this work quite recently, and so you get a sort of uniform way of describing some of the important sort of inference architectures that have been developed for various kinds of systems, including things like Bayesian networks and so on. So, and formally, the mathematics there is quite close to these sheaf ideas that I'm mentioning up there. The mathematical side, from my point of view, if we're looking at this variation over context, this is in the applications and sort of generally should be a functorial variation, so in the world of sheaves and pre-sheaves and so on. And these ideas have also been important in the semantics of computation over the last couple of decades. So I think there's a very interesting sort of paradigm there. How much time do I have left?
Another 10 minutes.
10 minutes, okay. Well, actually we've done propositional calculus and a bit of reality. So now let's look at another topic here. And this comes to some speculative ideas in biology that I think may be somehow interestingly connected with some classic topics in recursion theory and other things of computational interest. There's a sort of visionary thinker from a few decades back, Robert Rosen, who's sort of somewhere, in some superposition, perhaps of being a sort of great visionary of the subject and maybe of sort of speculation, but whose work continues to arouse considerable interest, and particularly had this notion of metabolism repair systems, which started already in the late 50s and used abstract mathematical ideas in a biological context in quite a remarkable way. So that one of the clearer expositions of this that I found is in some work of by some of these, well, we know Giuseppe Longo, sort of in logic and computability theory, and the other, I think his co-authors there are biologists. So this showed up in the Journal of Theoretical Biology a couple of years ago. So here's a sort of very quick look at these Rosen ideas. So in some sense, we're looking for structural conditions which are characteristic of, of systems endowed with life. One of the essential features of which is that they're systems that in some sense have a purpose. They try and maintain themselves. So biological systems replicate them, both try and maintain themselves and try and replicate themselves. So focusing on the self-maintenance aspect, so at the first level, we have a sort of, you can think of some abstraction of a basic metabolic process where we get some resources from the environment and we sort of generate the sort of biological network in which the metabolism is expressed. But then we know that these components wear out, so it is a general feature of biological organisms that there has to be a repair mechanism. This is continually going on in living things. So a repair mechanism can be seen as some kind of operator phi, which is able to regenerate the metabolic process F itself. So we get this kind of, whatever this equation means, this is the sort of idea. Now, Rosen's key insight here is that, you can ask a question then, well, if there's going to be a basic metabolism and repair, well, the repair mechanism will also wear out over time, so what do we do about that? So how will we repair the repair? So we need some kind of mechanism, say beta, to repair phi, but we seem to have some just some infinite regress, and it seems hopeless. And Rosen's answer is rather remarkable, I think. Is to postulate that beta is given by what we already have. It's already implicit in the original operation of the mechanism itself, and beta is actually given by this B equals Fa. So the equation then is that B applied to F gives us back the repair mechanism phi. So we get this loop which keeps the organism going in a self-sustaining way at the cost of some, as you see, of some circularity or reflexivity. So this is what is known in his work as closure to efficient causation, which a lot of people have been trying to understand. So one can ask, well, does this even make sense? Can we find a mathematical setting in which it makes sense? So this recent paper by Longo et al. gives an analysis in rather familiar terms that shows that, well, I mean, it may or may not be the way that biology works, although once these kind of ideas are put forward, they have a certain kind of sense to them, but at least we can make mathematical sense of it. So we have these functional equations, which look pretty hair-raising. In a sense, they are pretty hair-raising, if you try and figure out what the types are. So let's wrap it all in one big equation. The thing that would give us, if we just sort of, we can use these equations to eliminate everything. So we're given an A, which is the sort of material coming from the environment. So the kind of process F that we would need, which would satisfy this closure to efficient causation, would have to satisfy this equation if we eliminate the other variables from those equations, right? Which, remember, were motivated by the idea we have the repair mechanism that can regenerate F, and then somehow we can even repair the repair mechanism using the process that we started off with. So we get this fixed point equation for this process F. Now, where in the sort of wilder streams of logicians might such a thing exist? Well, it exists in the lambda calculus perfectly fine, because this is a functional expression. So if I write this expression G here, then the F that I'm looking for is exactly a fixed point of G. And everything makes perfectly good sense in the setting of the lambda calculus, and we can get I mean, we can get these operators satisfying all the equations. And what this may hint at is that there is some kind of reflexivity or circularity of this kind going on in biological mechanisms. It may be a hallmark of them. Now, one interesting point here is it isn't just a matter of having fixed points. So we can have fixed points in, we can add fixed point operators, and we standardly do in regular functional programming languages, whether implicitly or explicitly, although the types remain quite simple. But if you look at this G that we're taking the fixed point operator of, and you try and type it, you can see that the most general type here, if you followed Hindley-Milder type checking, would be an extremely recursive type. Recursive in the worst way, meaning recursive on the left side of the function types. It would be a T that would have to be equal to something like A arrow, T arrow, and then T arrow a couple more times, and then eventually escaping in some type variable. So the simplest way of putting it, of course, in the type-free lambda calculus, you just have a type T which is equal to T arrow T, and you have done with it, and then of course there are no type distinctions and everything is fine. The point here is that not just that this is showing that this kind of mechanism with this kind of closure property needs some recursion, but it actually needs self-application, which is a whole higher form of this. Self-application is something that's been in principle known to be a resource for computation for a long time, thinking both of the lambda calculus and the Kleene recursion theorem and so on, but is actually used relatively seldom. One of the nicest, most beautiful applications that do exist is the compiler, and partial evaluator line of ideas, originated by Futamura and others and developed by Neil Jones and other people. But it doesn't have a big imprint in current computation, but maybe we'll need to understand more of it to understand a wider range of things. So this gets us into this, this wider issue of reflexivity. So I was just talking at a coalgebra meeting and pointing out that coalgebra is a very interesting mathematics of reflexivity, but again, it doesn't encompass self-application. And it would be interesting to get a clearer understanding of the boundaries of what does essentially need self-application and what doesn't. And something I've been I mean, as I say, the Kleene recursion theorem is a huge resource for computability theory, but actually very little exploited, it seems to me, in computer science. And I wonder if there are some things to be understood there. So, in fact, there are two recursion theorems, and the extensional one is, of course, very widely used in computer science, in various elaborations. The intentional one, hardly at all. But I think there are some. I think the intentional level is one that there's still a lot potential in and a lot to be understood. Okay, so to finish up, because again, it's all Benedict's fault, and so he said I should talk about what I want to work on while I'm here. So how would I explain this? I was actually hoping that Barry would have been here because I think he would have appreciated this particular slide, but anyway, he isn't. So depending on the funding agency, so being a little bit more serious about some of the things I've been mentioning, so if we go back to the quantum topic that I started with, so we saw that, if you like, some structural way of understanding some issues about non-locality and contextuality, and I think arising out of that, there are some new ways of looking at the issue of classification of quantum states, which is one of the major topics in quantum information. People are still trying to understand the structure of entanglement. We know that entanglement is a key, presumably the key quantum resource for information processing point of view, but particularly when we get beyond bipartite entanglement, beyond two-party entanglement, very little is actually understood about this. And I think there are potentially some new tools here for addressing that. There's been a lot of interest in that community recently in something called the Pusey-Barrett-Rudolph theorem, which is about the status of quantum states. Can quantum states be understood merely as states of our knowledge, or do they have to be understood intrinsically as physical information? And the sort of direction of this PBR theorem is towards the latter point of view. And I think this leads to a sort of further agenda that has quite a natural computer science reading, which is that in some sense is quantum mechanics uniquely determined as providing exactly the minimal information required to produce its own empirical predictions, which would be in some sense a kind, because people have been of course looking for alternatives, things that are easy to understand from a classical point of view, possible extensions or ways of resolving various interpretational issues, ways of connecting quantum mechanics and gravity and so on. But is it given that we accept its empirical predictions, does it give exactly the minimum information within its formalism that's needed to do that? So in computer science terms, that would be a kind of full abstraction theorem for quantum mechanics. And I mean, as Fokyon mentioned, sort of wanting to get a paper written during his stay here. I've also got a paper that needs to be written, which is for a distinguished database collection for a distinguished database researcher. And what I hope I've convinced you is that the sort of thing I have in mind, which in some ways connects databases, Bell's theorem, and even a little bit of sheaf theory, actually makes perfectly good sense. Anyway, these are some of the things I'll be hoping to think about during my time here, and I'd be very happy if anyone was interested in any of these and wanted to have a chat about them. So I'll finish there. Thanks.
Some questions, please. Yes, John.
Could you explain a little more about your distinction between intentional recursion theorem and extensional? I don't quite get it.
Oh, well, maybe so I don't quite know the numbering and the nomenclature, but clearly have two recursion theorems. There's the thing we usually, the one which is where you get this least fixed point of an extensional operator, and that is the prototype for a theorem that has enormous applications in semantics of computation, least fixed points and all of that, complete partial orders, domain theory. So that's a prototypical theorem that's used to explain recursion, where you're thinking of recursion as an operation directly on functions understood in extension. The other one is the one about a sort of fixed point on codes, which is about things like producing programs that produce themselves as their output and all of that. So the intentional recursion, the fixed point theorem on codes.
This is what we call usually the second recursion.
Yes, I think it's the second, or yeah.
There is an article by Moskovakis.
Yes, a beautiful article, Kleeny's amazing recursion theorem.
Kleeny's amazing second recursion theorem. It's in
Right.
the bulletin last year.
And you see, it lists numerous applications within mathematical logic.
Right.
But I think one has to look quite hard to see anything much by way of applications in computer science. And my sense is that there could be some very interesting things to say in a more computational and also a more kind of modeling respect with that. As I say, the one place where, not the Kleeny recursion theorem, but at least some of the sort of pieces that go towards that, the SMN theorem essentially, is in this partial evaluation and metacompiler literature. Yeah, so I think that's what I mean. Yeah.
Any more questions, please, or comments? Yes.
Could you say something more about the connection to dependence logic? Is it, are you putting probabilities on dependence logic, or are you?
No, dependence logic is taking the probabilities out. It's only looking at the qualitative dependencies. Now, one of the interesting points with these foundational things in quantum mechanics is that many of the arguments can be done without probabilities. So I showed you a table where in the end you had to do a calculation to see what the weights were and see that the inequality was violated. But there are other cases where you can demonstrate that an inequality is violated just by knowing the support of the probability distribution. And even cases where you can tell that it's maximally violated by just knowing the support of the probability distribution. And these have been studied as, Bell's theorem without inequalities or without probabilities or by all versus nothing proofs and so on in the quantum foundations literature without any link with logic. But what we see here is you actually get a hierarchy of strengths of non-locality result, and some of them are directly accessible to relational arguments. So I actually had an earlier paper where I did some of those arguments, and that made part of this connection with Yoko's work. And we actually, so one of the things he's been doing is to show that you can use dependence logic as a nice setting for deriving many of these results. But also there's been a kind of influence because some of the ideas of independence, I think there were some suggestive things about these sort of physical arguments that because a lot of them hinge on, so the idea of Bell locality, for example, and no signaling and other such physically important conditions, when you translate them into this purely relational format, they start to look like interesting logical conditions, and then they fed into some of these different dependence atoms that are appearing in recent versions of
on the other hand, as we understand it now, dependence logic is another syntax for existential second-order logic. So is it the syntax itself that gives you more direct information? Could you do all these things in existential second order?
Well, so of course, model theoretically that's true. I'm not sure about succinctness issues and so on, but what we know is that the right that the power of a good notation, to refer to Whitehead, I think. So it certainly seems that it's sort of it's currently the focus of a lot of interesting work coming from different streams, and some things that maybe probably wouldn't have occurred to people to do has been coming out of that. For example, there's a recent inference system for the first order consequences of dependence logic, which of course isn't axiomatizable in full, but it has nice fragments that are, in fact. And actually I actually wrote a paper with Yoko a couple of years back where once you start looking at this semantic paradigm, a lot of other interesting things happen. So you can introduce a number of other propositional connectives. Actually there's a very natural interpretation for intuitionistic connectives in the original semantic framework for this. And then you get some rather nice things. For example, once you have the intuitionistic implication there, then the dependence atoms themselves are reduced to the apparently trivial constancy predicate. So the constancy predicate says that in any given that a particular field has to have a single value within a relation. So that seems like not very useful. But as soon as you combine it with the intuitionistic implication, you get the whole dependency notion back. And in fact, once you look at it from that point of view, one can see that the Armstrong axioms for dependence are exactly correspond to a standard axiomatization of intuitionistic implication. That's my discovery in database theory. I'm quite proud of that.
I wish Eric Randall had said that last week when he gave an invited talk in the database conference I attended on dependence logic, and people asked him about the Armstrong axiom. So that's very good.
Yeah. I think there are other connections with other notions of dependency that are coming through in other work.
Thank you very much. Let us thank the speaker again.